First of all, I would like to thank the organizers for the opportunity to give this presentation. Today, I will be describing this work where we have introduced relativistic reduced density matrix functional theory. Everything that I will comment in this presentation or I will present in this work, you can find in these slides. It's been published and you can find the publication from this year. We may wonder, why should we want to use REMFT or standard applicabilities? We have seen very nice talks where people are extending the applicability of REMFT into describing superconductors, bosons, and now into the relativistic domain, because we know that it's a really good way to account for correlation effects. Usually it was for non-dynamic correlation effects. Now it is also for some dynamic correlation effects. So if we want to introduce relativistic REMFT, the first thing is that we need to change the paradigm, and we need to move from the Schrodinger equation to the Dirac equation, where we have a first term that accounts for the kinetic energy and the rest mass energy, where this term is built with the Pauli matrices. And we have now a non-local external potential, which fulfills this condition to have real energies. And this is the problem for one single particle. If we solve this problem, we will obtain a 4-component spinor that is built from scalar functions, and that are usually just put together as a large component and a small component, coupling, let's say, taking these two parts, for example, for the large and these two for the small. We have the conjugate transpose of this guy that looks like this. And then we know that the solutions form an orthonormal basis that we can use to build our field operators. Like, for example, we have here our creation operator for the field, where we have a creation of electronic states, but annihilation of these negative energy states. And then we have the annihilation operator that, in this case, annihilates electronic states and creates negative energy states. So after their interpretation, the negative energy states that I will use in blue through all this presentation correspond to positronic states within QED. So if we want to move from one single particle to many particle problem, we just go into the Fock space, where we have the same operators as before, the kinetic energy, the interaction with external potential, and now we have to define this one particle density matrix operator using our field operators. And we arrive using these field operators to this very simple expression for the one REM, for the one particle density matrix operator, where we have one term that accounts for electronic term, electron-positron, and some positronic term. We want actually that the energy of this Hamiltonian, when sandwiched with the vacuum, to be equal to 0, and we therefore need to use the normal ordering in order to make the energy of to take the normal ordering in order to make this energy of this Hamilton of the vacuum be equal to 0. We know then that this Hamiltonian that we just defined commutes with the charge operator, where the charge operator is nothing but the sum of the charge of the operator for the electronic states and the minus the positronic states. So it will just give us the difference between the number of electrons and the number of positrons. And thanks to this commutation, we know that we can split our Fock space into different charge sectors. And therefore, and now let's suppose that we have our given a starting basis set, and where we have expressed our Hamiltonian, and we want to find another representation where this non-interacting Hamiltonian is diagonal. So what we will do is we will apply a Bogoliubov transformation. And then using this transformation, we could rebuild or rewrite in another way or field operators. In this case, for example, the annihilation field operator using this new basis and the new operators, creation and annihilation operators. But then we want to take again the normal ordering in this basis with respect to the new dress vacuum. That means that when we introduce the normal ordering, the energy of this vacuum for this Hamiltonian is 0, same for the rotated one. But then if we swap the Hamiltonians, we realize that this energy is no longer 0. And this is what is known as vacuum polarization energy. Within the vacuum polarization energy, we can compute it by defining this vacuum polarization 1 RDM, which is nothing but the difference of the negative energy states, all of them, for the new basis minus the one with the initial basis. So whenever we need to apply orbital or rotations, like for example to diagonalize a Hamiltonian, etc., we will have these vacuum polarization energy contributions. And this is very complicated because when we change the geometry, we will already have vacuum polarization effects. This is what it means. Now, let's include an extra term. Let's include the fermion-fermion interaction. In this work that we have in here, we just work with the Coulomb, including the Coulomb and the Gaunt interaction, where the first term accounts for Coulomb electron-electron repulsion, and the second term includes some current interaction between the electrons, current interaction. But now we will need, since this is a two-body operator, we need to define the second order reduced density matrix using again the same field operators and taking the normal ordering. It's easy to check that this Hamiltonian, including the interaction, still commutes with the charge operator. And therefore, we can actually minimize our energy for all wave functions for a particular charge sector for this Hamiltonian. So if we have a charge sector greater than 1, as we are usually interested in when we have an electronic systems, for example, we will have initially to build our wave function a linear combination of all possible Slater determinants. So this is like our usual full CI at the non-relativistic level, but we will need to include extra terms that account for the creation of positron-electron pairs. So we have here one extra electron-positron pair, here we have two extra terms, etc. Then we can compute the 1 RDM for this system, which actually just with the one value operator, and we will arrive to this expression where we have electronic terms, mixed terms, and positronic terms. It's nice to know that we can diagonalize this thanks to the hermiticity of the 1 RDM, and then we can obtain the natural orbital representation for this 1 RDM, where now a funny fact is that the occupation numbers go from -1 to 1 because we want that the sum of the occupation numbers to produce the charge. So we have all the ingredients we can introduce within the constraint search formalism of functional that searches among all possible wave functions for a particular charge sector that reproduce a given 1 RDM, the constraint search functional. And then we can use this functional to introduce relativistic RMFT, where we will just minimize among all unrepresentable first order density matrices. This domain will need to be at some point specified how it works. But then now we have our electron-electron interaction terms that will, or fermion-fermion interaction terms that will be here, and all one-body interactions that are accounted by this term. In the particular case, when we have natural orbitals and occupation numbers, well, we will have a functional of the natural or spinors for component spinors and of the occupation numbers. And as a particular case of this functional is when we have a local potential, a local external potential, so we will have relativistic DFT. But now in the case of relativistic DFT, as it happens in the non-relativistic limit, in the non-relativistic domain, we need to include the kinetic energy also in the constraint search. So now, actually, the creation of electrons and positron pairs requires a lot of energy. So we would usually be interested only into occupying electronic states, but then we will restrict our wave function to just have electronic states field, but that means that we will need to find the optimal spinors for this wave function, which is called using the no-pair approximation. So within the no-pair approximation, we can define the 1 RDM that is very similar to what we usually have in the non-relativistic limit, just formed by electronic states. But as I said, we will need spinor rotations to optimize these spinors, and therefore we will have vacuum polarization effects. So after plugging all this information, we can build a functional for the 1 RDM, for the no-pair 1 RDM, including these vacuum polarization effects, where we account for all one-body interactions with this first term in the first line, including for the 1 RDM and for the vacuum polarization 1 RDM. We have two terms that account for interactions between our vacuum polarization 2 RDM and the no-pair 1 RDM, which are of Hartree and exchange type. This is usually known as self-energy as well type. And then we have an extra term that is like Hartree and exchange type of this vacuum polarization 2 RDM. This vacuum polarization 2 RDM is nothing but the Hartree-Fock or the single determinant approximation, sorry, for the 2 RDM using the vacuum polarization 1 RDM. And there is this one last term that is unknown, and it's just the particle-particle interaction in terms of the no pair 1 RDM. So how do we need to approximate this guy, and that's the purpose of the rest of this work. So usually when people work with in the relativistic domain, everyone neglects the effect of vacuum polarization effects, and this is the usual application of the no pair approximation. So what do we know about the guy that we need to approximate? So it is actually a functional of the 2 RDM of the second order density matrix that we can build, that we can write like this. But then, as it is usually performed in the non-relativistic limit to construct energy functionals, we will probably Professor Shevsky will already complain about this, but we will have these just occupation numbers to build. We will use as the occupation numbers to build the 2 RDM elements. But then we will impose again the usual representability conditions, and we will impose that the trace is the correct trace, and that these functionals, the ones developed, retrieve their non-relativistic counterparts in that corresponding limit. So something about notation. We have this for the one electron integrals, this for the usual Coulomb electron-electron repulsion integrals, and then we have this for the Gaunt interaction, the one that accounts for currents. And then we know that in non-relativistic natural orbital functional theory, usually it's a restricted formalism is employed. And this can be achieved in the relativistic context by using Cramer's pairs. So what we will do is we will impose that our natural orbitals behave as Cramer's pairs, which means that when we apply this time reversal operator, we have this relationship among the spinors that will be degenerated. And then we will only retain, when building our functional, only up to 2 different indices to account for Hartree, exchange, and some correlation effects. And finally, we will just build functionals for the case when the occupation numbers are the same for the, let's say, bar and unbar states. The ones that will, in the non-relativistic limit, corresponds to alpha and beta states, in other words. So this is the first function. This is the expression that we arrive to when we only retain up to 2 different indices. And the elements in orange are the ones that we need to approximate as functions of the occupation numbers. And we can take, for example, the Dirac-Hartree-Fock approximation, where occupation numbers, which takes exactly the same expression as in the non-relativistic limit. And then we plug it into this expression in here, and we would obtain this energy expression, where in the case that occupation numbers are 0 and 1s, as usual, we will have just a very simple expression. I would like to ask you to keep in mind this red term because it will come up later. So we could also build the relativistic version of the Mueller or the power functional or any of the JK only approximations. To that end, we will just need to change what is in front of the exchange contribution. And then we would arrive to the relativistic version of the Mueller, the power, etc. functional approximations. But a funny fact is that in the relativistic domain, there is exchange of opposite spin terms. And that means that, for example, an element that in the non-relativistic limit for the 2 RDM that will be alpha beta has exchange in the relativistic domain. So therefore, we could use another function to account for this opposite spin exchange that with a function that could be anything, right? And finally, then we could also write the relativistic expression for the pin of 5, pin of 7 functional approximations, where we will have to account, as we know, for intra and inter-subspace interactions. For the intra-subspace interaction, we have this energy expression written in here that is very, very similar to what is used in the non-relativistic limit. And we know that this functional corresponds to the fixed phase functional that should be almost exact for the 2 electron systems, except for these phases in here. Then We need to account for inter-subspace interactions, and we will have first initially the term that I ask you to remember this Hartree-Fock-like interaction. In that case, we will have a pin of 5, relativistic pin of 5. If we include extra terms to account for electron correlation, we would arrive to pin of 7, pin of 7s, etc. So we know that this functional, in the case of relativistic pin of 5, we have proven this, that it corresponds to a relativistic version of APSG, which then should be fully unrepresentable. So as conclusions for this work, I have introduced relativistic reduced density matrix functional theory within the constraint search formalism and allowing the creation of electron-positron pairs. Then I went into the no-pair vacuum polarization approximation of relativistic reduced density matrix, where we only fill positive energy states, but include for vacuum polarization effects. Finally, I have introduced just the no-pair relativistic RMFT, where we only fill this, but neglect vacuum polarization effects. It's worth to tell that actually the current or the current can be written as explicit functional of the 1RDM, which means that a functional of the 1RDM contains more information than the functional of the current. Then imposing Kramer symmetry and some other conditions, we have built the first relativistic versions of some functional approximations. And as a future perspective, I'm trying to implement this in Dirac code. Some open questions that are now on the list. For example, the problem of spinor optimization. In this case, we need to apply a min-max procedure because, as we can see, for example, these are Dirac-Hartree-Fock calculations. This is a Dirac-Hartree-Fock calculation for helium atom. This is the total energy using this dial double zeta basis. And as we can see, the energy of the states, here I have in blue the negative energy states, the ones that correspond to positronic states. And this is the orbital that is occupied, which is the first, let's say, electronic state. And this is at Hartree-Fock level, of course, and the rest are the virtual orbitals. This means that we need to optimize and to find this saddle point in the optimization procedure, which is quite tricky compared to the non-relativistic limit. And second question that it's open is that I presented that we can account for vacuum polarization effects. In fact, this one, the so-called small component of the spinors, can be written as functions in terms of the large component. And this is known as the restricted Kramer's restricted kinetic balance. But in the case of the restricted kinetic balance, this is what is used in Dirac code, the code that I'm using for implementing this. And we can rewrite the expression for the vacuum polarization 1RDM in terms of the current basis as the difference between the positive energy states minus the negative energy states. For the case of the free particle, the density that comes out of this vacuum polarization 1RDM should cancel because the states are the same for positive and negative energy states. By using this restricted kinetic balance, that is the one implemented in Dirac, we will have that these terms do not cancel. And this is taken from the thesis of Dr. Maen Salman from University of Toulouse. In this case, we need to apply another type of kinetic balance, the dual kinetic balance that will account for the correct charge conjugation of the states. And this is something that will also need to be taken into account when we will use our functional for accounting for vacuum polarization effects and the no-pair within the no-pair approximation. So with this, I would like to thank you for your attention. I would like to thank Professor Vischer and Luke and Klaas Gisbert for their support, and all of you for your kind attention.